Hello, my name is Ryzhikov and I'm presenting the talk Synchronizing Strongly Connected Partial DFAs, which is a joint work with Mikhail Berlinkov, Robert Ferens and Marek Szykuła. First I will describe the setting of synchronizing complete DFAs, and then I will proceed to the goal of our work, which is generalizing this setting to synchronizing partial DFAs. By a complete DFA, we understand simply a finite set of states, a finite alphabet, and a complete transition function, which tells us for every state and every letter where this state should go by this letter. A word is called synchronizing for a complete DFA if it sends all states to the same state. A complete DFA admitting such a word is also called synchronizing. The concept of synchronization is essentially the concept of regaining control over some system. If we know the structure of a system but we don't know its actual state, then we can apply a synchronizing word, and since it sends all the states to the same state, we know after the application of this word the actual state of the system. This concept is used in various areas of computer science. For instance, in coding theory, in orienting parts in manufacturing, and so on. Let's look at some example. We start with all the states active, and we apply a word letter by letter to this automaton. So we start with applying the letter A, which sends the state 1 to the state 2, and the state 2 to itself, and the state 3 to itself. Then we apply the letter B, then we apply the letter B again, and finally we apply the letter A, which sends all the states to the state 2. So we know that now the word ABBA is synchronizing, and hence the automaton is also synchronizing. One of the most important problems about synchronizing automata, and one of the oldest open problems in automata theory in general, is the Cherney conjecture, which goes back to 1964. It says that for every synchronizing complete DFA with n states, there is a synchronizing word of length at most n-1 square. In 1971, Pan showed that there is a cubic bound of n cubed minus n over 6 for this value, and for many years that was the best known upper bound, until recently when Szykuła improved it further to a smaller cubic upper bound, and then Szykuła a year later improved it a little bit more. However, there is still a gap between the cubic upper bound and the conjectured quadratic bound. The reset threshold of a synchronizing DFA is the length of its shortest synchronizing word. And Cherney showed that there is an infinite series of synchronizing binary complete DFAs with reset threshold equal to n-1 square. This means that the Cherney conjecture is tight if it is true. And the automata in this series have a very simple structure. They have a cycle by the letter B, which goes through all the states, and the letter A maps every state to itself, except for the state 1, which is sent to the next state on the cycle. The rank conjecture is a generalization of the Cherney conjecture from the case of synchronizing word to the case of words of arbitrary rank. By rank of a word, we understand the size of the image of Q under the action of this word. So this means that if we start with the set of all states and make all these states active, then after applying a word of rank R, we get exactly R active states. The case of synchronizing words is exactly the case of words of rank 1, which means that a word is synchronizing if and only if it has rank 1. The rank conjecture says that for an n-state complete DFA, where R is the minimum rank over all words, there exists a word of rank R and of length at most n-1 square. So we can see that if we take r equals 1, which is exactly the case of synchronizing words, we get exactly the Cherney conjecture. In 1983, Pan showed a cubic upper bound on the length of shortest words of rank r. However, obviously, we cannot get any subcubic upper bound for the rank conjecture unless we get a subcubic upper bound for the Cherney conjecture. So this case is even more difficult than the Cherney conjecture, which is still open. Now we move to the case of partial DFAs. By a partial DFA, we understand a finite set of states again, a finite alphabet, and now we have a partial transition function, which means that for some states and some letters, we could have undefined transitions. For instance, in our example, we see that for the state 1, the transition labeled by the letter A is undefined. The case of partial DFAs is important in modeling in the following situation. Assume that we know the structure of a system, and now instead of applying some words to it, we just observe the input of the system with a guarantee that no undefined transition is taken. So we could still not know the actual state of a system, but we see its input and we know its structure. We would like to learn at some point the actual state of the system by just observing the input. And if we are able to generalize the setting of synchronizing words from complete DFAs to partial DFAs, then this would help us to learn the actual state of this system. There are several different definitions generalizing synchronizing words from the complete to the partial setting. One of them is the setting of carefully synchronizing words. A word is called carefully synchronizing if it maps all the states of an automaton to the same state. So this means in particular that this word has to be defined for every state of the automaton. However, it occurs that this setting is too restrictive, and in most natural subclasses of partial DFAs, we get exponential behavior. By that I mean that we get exponential lower bounds on the length of shortest carefully synchronizing words, and also in most cases the problem of just checking if a partial DFA is synchronizing is p-space complete. However, we would like to find some setting with nicer behavior, which is more similar to the case of complete DFAs, where we have, for instance, polynomial upper bounds on the length of shortest synchronizing words. And another way of generalizing synchronization from the complete case to the partial case is the following definition. We call a word W synchronizing if the size of the image of the whole set of states under the action of W is 1. So this means that this word can be undefined for some states, but it has to collect all the states for which it is defined in the same state, and it has to be defined for at least one state. So we can see in particular that every carefully synchronizing word is synchronizing, but we have synchronizing words which are not carefully synchronizing because they can be undefined for some states of the automaton. This definition is in fact a particular case of a more general setting of synchronizing unambiguous automata, which are used a lot in the theory of variable length codes. And as we will see at the end of my talk, there is a direct application of this setting to the case of synchronizing prefix codes. If we look at the general case of partial DFAs, we still get some properties which are not very nice from our point of view. So it is possible to show that checking if a partial DFA synchronizing is p-space complete, and there is still an exponential lower bound on the length of shortest synchronizing words. However, there is a very natural class of partial DFAs where we get behavior similar to the case of synchronizing complete DFAs. So first, let's look what makes the case of partial DFAs different. If we want to synchronize a complete DFA, and if we look at the behavior of pairs of states during the synchronization, we have essentially only one scenario, which is merging a pair. So imagine that we start with all the states active, and then we want to decrease the number of active states. To do that, we take a pair of active states and we send them by some word to just one state. This way, we're able to merge this pair and so to decrease the number of active states. However, if we are synchronizing a partial DFA, then we have two different scenarios. So once again, we start with the whole set of states as active states. But now if we pick a pair of active states, we can either merge this pair, just as in the complete case. So we take some word which maps both these states to the same state. Or we could kill one state of a pair, which means that we find a word which is defined for one state of the pair and is undefined for another state of the pair. So by applying these two operations of merging a pair and killing one state of a pair, we could hopefully synchronize our automaton. Now we need to know which of these two operations to use and which pairs of states to pick. So this is, as we can see, a much more general setting, and we need some additional tools and some additional results to deal with these two options. So let's come back to defining a class of partial DFAs where the behavior of synchronizing words is polynomial. An automaton is called strongly connected if for every pair P and Q of its state there is a word mapping P to Q. And strongly connected automata form a very important class of automata. For instance, if we're modeling a reactive system, it is natural to assume that we can return to any state of the system after any given moment of time. The same is true for the case of decoders of prefix codes. So every decoder of a prefix code is a strongly connected automaton. It is possible to show now that a strongly connected partial DFA is synchronizing if and only if every pair of its states can be mapped to a subset of size 1 by either merging it or killing exactly one state of the pair. This is exactly the behavior which allows us to show polynomial upper bounds in the case of complete DFAs, so that gives us hopes that we can also get some nice polynomial upper bounds in the case of partial DFAs. And we will see that indeed, if we restrict ourselves to the strongly connected case, we can transfer many results from complete DFAs to partial DFAs. To deal formally with the two options of decreasing the number of active states, we introduce the inseparability equivalence. This is an equivalence relation on the set of states of the automaton, and it simply says that two states are equivalent if and only if for every word either this word is defined for both of these states or it is undefined for both of these states. In other words, this means that there is no word which is defined for exactly one state of this pair. It is possible to show then that we can send the whole set of states to one inseparability class by a word of at most quadratic length. So this is nice in terms of the Cherney conjecture, for instance. And then we can reduce this problem to synchronizing this inseparability class to one state. In this case, we can only merge pairs of states in this class because just by definition of the inseparability equivalence, we don't have any words which can kill one state of a pair, but we get an additional restriction that all the words we use must not kill the whole set of active state. So we can use only words which are defined for at least one state of our inseparability class. And this introduces a lot of additional difficulties in dealing with synchronization of partial DFAs. So one particular thing that we study is how to deal with these issues and how to reduce our problem of synchronizing a partial DFA to the problem of synchronizing a complete DFA. What we would like to do is to find some reductions which allow us to take a synchronizing partial DFA and to make a synchronizing complete DFA out of it in such a way that the length of shortly synchronizing words is preserved or approximately preserved. The first tool for achieving this goal is what we call the fixing automaton. A natural idea if we take a synchronizing partial DFA and we want to get a synchronizing complete DFA out of it is the following one. If we have some undefined transitions in our partial DFA, we can define self-loops instead of them. And the fixing automaton is a complete DFA obtained exactly by adding self-loops instead of undefined transitions in our partial automaton. So in our example, we see that the letter B is undefined for the states 3 and 6, so we can define self-loops by this letter. What we get is then a complete DFA. However, the problem is that it's not necessarily synchronizing. And to get some results by using this construction, we need to ask for more guarantees than just guarantees on the length of a synchronizing word. But we know that we have the rank conjecture and we have some results about rank conjecture, so we can use it for dealing with this issue. And we show that if we start with a strongly connected partial DFA, and if the rank conjecture holds for the fixing automaton of this DFA, then it also holds for the original partial DFA. This shows that the rank conjecture is true for strongly connected partial DFAs if and only if it is true for complete DFAs. So any improvement for the rank conjecture for complete DFAs would mean also an improvement for strongly connected partial DFAs. Let's look at some particular usage of this result. A classical class of complete DFAs where the Cherney conjecture is true is the class of Eulerian automata. These are automata such that the number of outgoing and incoming transitions are the same at every state. And a classical result of Curry says that the Cherney conjecture is true for this class. Moreover, it was shown recently that the rank conjecture is also true for this class. And now we can use this result to show that for partial synchronizing Eulerian DFAs, there is an upper bound of n-1 square on the length of shortly synchronizing words. Now, if we want to deal with the case of synchronizing complete DFAs and to transfer results directly from this case to partial DFAs, we need a more involved construction. For instance, what we would like to show is that there is an analog of the Cherney conjecture and there are similar upper bounds for the Cherney conjecture in the partial case as there are in the complete case. To achieve that, we use the construction of a collecting automaton. So we start again with a strongly connected partial DFA. First, we construct a fixing automaton of this DFA, and then we add some additional letter which makes this automaton synchronizing, but it has an additional nice property that it creates no shortcuts, which means that the length of shortest synchronizing words for this automaton is comparable to the length of shortest synchronizing words for the original partial DFA. For doing that, we look at the inseparability classes of our automaton. So in our case, we have three classes: the class of the states 1, 4, then the class of the states 2, 5, and the third one of the states 3, 6. And then we find some rooted tree pointing towards one of the classes. In our case, this tree has 3 nodes and 2 edges, one going from the class 1, 4 to the class 2, 5, and the other one going from the class 2, 5 to the class 3, 6. And also for the states corresponding to the class, which is the root of this tree, we add self loops. So we can see the transitions by the letter gamma from the state 1 to the state 2, from the state 2 to the state 3, and from the state 3 to itself, and the same for the states 4, 5, and 6. So, as I already said, collecting automata have a number of nice properties. So if we start with a partial DFA and we construct its collecting automatons, and this collecting automaton is synchronizing if the original partial DFA is synchronizing, and moreover they have comparable reset threshold, which allows us to transfer results about upper bounds on reset thresholds from the case of complete DFAs to the case of strongly connected partial DFAs. In particular, we show that if the Cherney conjecture is true, then every synchronizing strongly connected partial DFA with n states has a synchronizing word of length at most n-1 square plus something subquadratic. This shows a very strong relation between reset thresholds of complete DFAs and strongly connected partial DFAs, and moreover, the proof of these results also shows that if there is an improvement for the Cherney conjecture in the complete case, then we can also get, by using this result, an improvement for the strongly connected partial case. We also show that for algorithmic results, the situation for strongly connected partial DFAs is very similar to the situation for complete DFAs. We show that checking whether a partial automaton is synchronizing in the strongly connected case can be done in quadratic time, and finding a word of minimum rank can be done in cubic time. This is the same as in the case of complete DFAs. And also by using collecting automata, we can provide a very fast reduction from the partial case to the complete case, which means that if there is an improvement in an algorithm for checking synchronizability in the complete case, then we can also get a faster algorithm for checking synchronizability in the strongly connected partial case. Finally, let me describe an important special case of strongly connected partial DFAs, which is literal automata of finite prefix codes. A prefix code is just a set of words such that no word in this set is a prefix of another word. And so we start with a finite prefix code X, and we can build the tree of this code, as usually by taking the empty prefix as the root of this tree, and then the children of a node are obtained by writing a letter at the end of the current prefix of some code word. From this tree, we can get a literal automaton. So we get it by merging all the leaf states with the root state, and in such a way we get a partial DFA, which is obviously strongly connected. We show that a synchronizing partial literal automaton with n states always has a synchronizing word of order n times log cube n. This result was already known for complete literal automata. So complete literal automata correspond to maximal finite prefix codes, and the proof of the case of partial literal automata is even more difficult than the complete case, and I will briefly describe how we get it. The proof consists of two big parts. The first one is to show that, similarly to the complete case, in the partial case we can also use induced automata. So we show that if a partial automaton admits a word of linear length and non-zero rank of order log n, then its reset threshold is at most something linear times the reset threshold of an automaton B, where B is an automaton with a logarithmic number of states. In this case, we can then use just a cubic upper bound for the automaton B and obtain our upper bound. In the complete case, showing that there is a logarithmic word of small rank is quite easy. It is enough to look at all words of logarithmic length, and then it is possible to show that there is one such word which maps every state to the root state at some moment of time when we apply this word. The case of partial literal automata uses the same idea, but in this case the proof is much more difficult because now some words can be undefined for all the states of the automaton, so we have to additionally tune this idea to the situations where this happens.